Okay, with this last video, I just want to go over a little bit of a precursor to the Central Limit Theorem, which will be a topic that we'll discuss in our next class. This tends to be a sticking point, the Central Limit Theorem, so the more exposure, the more repetition, the more examples I can give you, the better. So here's the idea. Typically, in a statistical situation, we have a large population that's too big to kind of study in its own. So what we end up doing is we take samples from our population and we try to infer something from the sample. Now, in order to sort of speak about possible mistakes we might make by doing this sampling approach, what we often work with is something called the sampling distribution of whatever statistic we're going to compute. Now, in our case, we're going to be very interested in what's the sample mean as a reflection of what the true population mean will look like. And so we're going to be interested in something called the sampling distribution of sample means. And here's sort of a crude way of how you might create or get an idea for what a sampling distribution of sample means truly is. The idea is we want to figure out what would happen if I fixed a sample size. So let's say I'm going to sample 50 people when I do my statistical study. So n in this case is going to be 50. What would happen if I took a number of different samples? Okay, so maybe I'm 300 different research teams. The first research team collected a sample size 50, we call sample 1. A different research team has a different sample, same size though, size 50 observations, etc., etc. Each one of these different research teams is going to report a different statistic. All right, so research team 1 is going to have a sample mean called x bar 1, right? This is the sample mean for their particular sample. And the second research team is going to have a slightly different, they're not going to be the same, slightly different sample mean, okay? Now, each one of these will be relatively close to the true population mean, but what we're looking at is as our random samples vary, how does that affect the sample means that we actually see? In other words, what we want to do is think about this as a data set and ask some standard questions, right? Where is this data set of possible sample means centered, right? Where is the middle of it? Or in other words, what's the mean of these sample means? How much variation do we see, which is a notion of the standard deviation of the sample means? And what kind of shape does it have, right? Is it a normal distribution? Does it have a left skew, a right skew? Is it uniform, etc.? So let's do a very quick simulation of what I'm talking about. Let's treat the set of scores up in the upper left-hand corner here as a population of values. It's not very large. We could study it in its own right, but let's just sort of play devil's advocate and play along here. Here's what this population of scores actually looks like in terms of its histogram. Here's the idea. What we want to do is think about, well, suppose I deem it too expensive to look at all these scores at once. So what I want to do instead is just select a small sample from the population. So when I click this select sample from the population, it highlights those scores that ended up being in my sample. And you'll notice here in columns L and M, it's going to label the sample number. So this is maybe like research team 1 found a sample mean of 50.42. Okay, I can click this button again, and research team 2 reports their sample mean. So research team 2 has a different collection of scores, and all led to a sample mean of 57.87. Right? And each time I click this, a new research team takes a random sample, computes a mean, and then reports it. And what we can see in columns L and M is just a collection of all the different sample means that these different research teams are reporting. Now there's a nice button here, run 100 samples. I'm going to click this a few times. And what this essentially does is now collects, I think, maybe 400 different research teams' sample means. So you can actually scroll down and see all of the different scores. All right. Now, if we move over to the right, again, we're considering this collection of different reported sample means as a data set. We can explore them using the techniques we've talked about this year. For example, what's the shape of the data? Well, here's our histogram of sample means. We can see it has a nice bell-shaped curve. In other words, it kind of lks like these sample means are normally distributed. If we wanted to, we could compute the mean of this data set and the standard deviation of this data set as descriptive statistics. And that's exactly what I did over here under the in practice. Right? The mean of this column of scores ends up being 53.75. And the standard deviation ends up being 4.07. Okay, so our sample means we know should have a roughly normal looking distribution with a mean of 53.7 and a standard deviation of 4. Now, this is done by actually simulating different samples from a population. What we're going to look at is treating our sample mean as a random variable, and we're actually going to make predictions based on what we know about the population. And this is what the central limit theorem is going to help us do. Now you'll notice this mu of x bar, sigma of x bar, these are the predictions that the central limit theorem is going to make. And this is what we achieved in practice by actually doing the simulations. And you can see how close the two means are. Here's the estimate, here's what we actually saw. Here's our standard deviation estimate, here's what we actually saw. So this here, this is our central limit theorem idea, is going to give us a reasonably good approximation for what we would expect these sample means, how they should behave, based on the parameters of our original population. In fact, you can see that these estimates by our cell references are based on what we know about the actual population. So the standard deviation for our sample means is going to depend on, well, what's the standard deviation in the original population? Right. So again, the main idea here is to treat the sample means that could appear as being a random variable, right? Each possible sample is kind of like rolling a die. You don't know what face is going to pop up. Just as if you sample from a population, you don't know which sample mean is going to pop up. So each sample mean, or the sample mean itself, can be treated as a random variable. A coin flip, a roll of a die. Once we know that x bar, this sample mean random variable, can be treated that way, we can ask our standard types of questions. What does this distribution look like? What's our expected value, or what's the mean of this random variable? What's the standard deviation of this random variable? And this is exactly what we explored with this little macro-enabled workbook. The distribution looked normal, and we can see that the central limit theorem predictions match up with what we actually saw in practice. Okay, so the central limit theorem is going to give us the answers about this sample mean random variable. Here's what the central limit theorem essentially says. Under certain conditions, if we draw samples of size n from a population with a population mean mu and a population standard deviation sigma, so these are in green because they're coming from our population, then our sample means, these are in blue, we're talking about taking a sample and looking at the means. How would those end up be distributed? Have the following formulas. The mean of your sample means is the same as the mean in your population. The standard deviation of those sample means is corrected by dividing by the square root of your sample size. Okay, so for example, suppose the time spent on Facebook by employees at our company is normally distributed with a mean of 50 minutes and a standard deviation of 15 minutes. Okay, so this is for an individual employee. On average, we expect an individual to have a mean of 50 minutes on Facebook with a standard deviation of 15. Now, if we start working with a group and we select 10 employees, right? So now we're sampling a group of size 10 from a population, right? We want to describe what is the distribution of the sample mean random variable, okay? Now, the first thing the central limit theorem tells us is that both of these end up having a normal distribution. Specifically, the one we care about is the sample mean random variable. Now, in the population, the mean is 15 minutes. For the sample means, we end up with the same mean. So on average, even that group of 10 is going to have a mean of 50 minutes. Now, for individuals, we see a standard deviation of 15. For the group of 10, right, for the samples, we're going to see a standard deviation of 15 over the square root of our sample size, or over the square root of 10. So we're going to have a much smaller standard deviation when we work with the groups of 10 as opposed to with individuals. Okay? So I'm going to go over one more example, and I'm going to show you how we can actually use this central limit theorem with these updated parameters to start answering some questions about probabilities. So back to our week 7, day 1 worksheet. We're in our final CLT example sheet, and here's the problem we want to consider. Suppose carrots at the supermarket have a mean length of 8 inches with a standard deviation of 1.5 inches. Assume the length is normally distributed. Okay, so these are individual carrots. Pick a random carrot at the supermarket. On average, it's going to have a length of 8 inches, but we're going to expect some variation, 1.5 inches on the individual basis. So population-wise, we have a mean of 8 inches, standard deviation of 1.5 inches, right? Now here's the critical part, all right? We want to select a group of carrots and sort of treat them as a unit. So if we select a group of 6 carrots from the supermarket and treat them as one group, what's the mean length for the group? We want to know what's the probability the mean length for this group falls between 7.5 and 8.2 inches, right? So we're getting 10 different carrots and then summarizing it into a single mean length for the group. Okay, so here we're dealing with a sample mean random variable, which we're going to call x bar. Okay? Now, according to the central limit theorem, we know a couple of things about the distribution for x bar. One, x bar is normally distributed. 2, the mean of x bar is equal to the mean in the population. All right, so the way we're going to denote this is mu of x bar is going to be the same as that in the population. So our mean here doesn't change, it's still going to be 8. Finally, the standard deviation of this sample mean random variable. So how much variation are we going to see in the mean length for groups of 6 carrots? Right? This is equal to sigma in the population divided by the square root of sample size. In other words, let me move this over one. Sigma of x bar is going to be equal to the 1.5 we got out of our population standard deviation divided by the square root of our sample size, which in this case is 6. Right? So 1.5 over the square root of 6 gives us some updated parameters for our x bar distribution. Okay? Now fundamentally what we're looking for is what's the probability, the mean length for this group. So what's the probability that x bar falls between 7.5 and 8.2 inches. All right, now notice this is a probability regarding x bar, not our original random variable. But we know that this probability is normally distributed. We have a mean and we have a standard deviation. So we can use our usual approach. We can think of this as x bar being less than or equal to 8.2. And then subtracting x bar being less than or equal to 7.5, right? So we'll treat this with our standard approach. We can convert these things to z-scores using our new parameters. So 8.2 minus 8 divided by our new standard deviation is going to be our z-score when we go to compute this probability. Same type of idea. Notice I'm using the new standard deviation. Right? So this would be the probability that z is less than or equal to 0.32, let's call it 6 or 7, minus probability that z is less than or equal to negative 0.816. And now we can compute each one of these using a norm.s.dist and finish the probability computation. So you have norm.s.dist true minus norm.s.dist negative 0.816 true. This is our probability. Okay, so as a group of 6 carrots, the probability that the mean for that group of 6 carrots falls in between these two values is going to be about 42%. And this is fundamentally what the central limit theorem allows us to do. Since we're sampling groups of a certain size from a population, it tells us about what the sample mean for a group of a specific size. It tells us how it should behave and allows us to use our probability techniques that we've already worked on so far this year to compute probabilities now speaking for groups rather than individual measurements. And this is the real power of the central limit theorem that we'll explore in class.